Gnanam paramam dheyam. Knowledge is supreme.
So last lecture I went on till the radial component of the hydrogen atom wave function, and I said they are given by the Laguerre special functions, right. So I don't want you to memorize. I was saying in the beginning of the class, nothing I want you to memorize. Whatever data is required, I will be giving it. You should be able to decipher what that data is and put it in your accordingly in your answers. Okay, so just to recall, I called Rn, capital Rn, and then there was a azimuthal quantum number L. So this wave function for the radial component is constrained by the principal quantum number as well as the azimuthal quantum number, and that is incorporated in your Laguerre, associated Laguerre function. So these normalizations are worked out already. So for simple cases, maybe for n equal to 1 or L equal to 1, you can verify what is happening. N equal to 2 and L equal to 1, you could verify this. Okay. So there is an equal to sign which is missing here. So this is a neat summation formula for the Laguerre functions, associated Laguerre functions, and you can try to substitute here and verify. So there is an equal to sign here. You can try to verify that you get R10 to be this, R20. Please check it out. Okay. So this is the radial part of the wave function for the hydrogen atom problem. And the energy eigenvalues also will be from this solution to that equation. You can read off what the energy is, and that is nothing but proportional to 1 over n squared. In electron volts you can write it as 13.6 electron volts. Negative sign because it is a bound state. So formally hydrogen atom wave function can be written as now with 3 quantum numbers, ml from the phi variable differential equation, and then L and ml together is going to be showing up in the theta part of the wave function, and then we have this principal quantum number and the azimuthal quantum number showing up in the radial part of the wave function. So you can list a few of them. The ground state wave function, we know what this is. This is 1 and this is m equal to 0. So these two are 1, and then there is a normalization, and you can also check the normalization. What is the normalization condition? This also I stressed last time. It is an integral over dV, and dV should be written in the spherical polar coordinates, which will have an r squared sin theta d phi d theta. So that integral has to be done. You can't blindly do d theta, d phi and dr and write the normalization. Okay. It is a volume integral, and if it is different coordinate, if it is Cartesian coordinate, it would have been dx dy dz, but because it is spherical coordinates, there will be a Jacobian factor, and you cannot forget the Jacobian factor. So similarly, so you can check the first and the second just for the get a feel on the wave function. You don't need to memorize any of these things, but check the normalization, whether you are able to reproduce, and check whether plugging in those general associated Laguerre functions, you can write this wave function and so on. Just please check it. Okay. So here whenever L is 0 and phi is 0, the quantum numbers corresponding to that, there won't be a theta phi dependence. But if suppose L becomes 1, then there will be a cos theta. If it becomes ml equal to plus or minus 1, you can have an e to the power of plus or minus im phi, where m is plus or minus 1. Okay. So you see that everything coming up from the Legendre, associated Legendre and so on. We called it as a spherical harmonics. So please verify these things. I will put the file today in the Moodle and you can verify. Also verify the normalization condition, which is integral of dV, which is r squared sin theta dr d theta d phi, and limits are also theta from 0 to pi, phi from 0 to 2 pi, and r is from 0 to infinity. And you can also use this gamma function integrals. This data and all will be given in the question paper if it is required. So this is the gamma function where n is an integer, and you can write this as an n minus 1 factorial. So you can also, this is something which I mentioned last time, that you can split that integral into 3 integrals, the dr integral with an r squared factor, and then sin theta with the d theta integral part, and phi has nothing. So each one you could try to normalize when you do this integration, and you can interpret them as probability of finding the particle between r and r plus dr, radial coordinate is this, theta and theta plus d theta is this, and phi plus d phi. Something wrong here. What is wrong? This has to be a capital phi of phi. I need to correct all these files, but I am announcing it, so please correct it right away, and when the file comes, it's still not corrected, but just remember. So clearly the energy eigenvalues are independent of the azimuthal quantum number and magnetic quantum number, right? Just like we did Landau levels, it tells you that this is also degenerate, but it's not infinitely degenerate. There is a restriction. Given an n, the differential equations put some restriction on L. L has to be n minus 1, can take values from 0 to n minus 1, and ML has to be from, for every L, it is constrained to be minus L to plus L. So these things comes from the differential equation. So that we cannot, so then you can actually tell what is the degeneracy for every principal quantum number. I am sure you have done it in chemistry. What is the degeneracy? It's just n squared if you don't include the spin quantum number, okay, but if you include the spin quantum number, you will have a 2n squared. So there's another thing which I felt you should know is that typically when we do transitions in the lab person, suppose he is looking at a state which is with energy En and psi n l ml, okay. So the En state has 2n squared degeneracy if you include spin quantum number, if you don't include it is n squared degeneracy. I am taking a specific state here. The question is whether this atom can, do a transition to any excited state or from the excited state to a lower energy state. Suppose I take another lower energy state as Em with psi m, probably this is not a very good notation. Let me put En1, En2, N1, L1, ML1. So N2, L2, ML2. Can this undergo a transition is the question. So then there are some selection rules, not all of them. There are these orthogonality conditions which will come in mathematics, but experimenter will try to look for a transition which corresponds to going from this set of quantum numbers to this set of quantum numbers, whether the transition is possible. So this is what is called as a selection rule. So when is it possible? Delta L, which is L1 minus L2, what condition on it when this will be allowed? Similarly, delta M, which is ML1 minus ML2, what are the conditions under which it will happen, the transition will happen. This is what is called as a selection rule, okay. So let me tell you first what is the data which the experimentalist tells us, and then we will see from our math or quantum mechanics whether we can reproduce that information. So right now that delta L constraint is given to be, experimentally they find delta L must be plus or minus 1 and delta ML has to be either 0 or plus or minus 1 is what they say. How do we verify? This is where that similar problem can help. So how do we understand the experimentalist data on the selection rule? To understand that, try to write an arbitrary state. I told you that this toggling cannot happen unless you write a superposed state. If it is in the stationary state, it will remain in the stationary state. Okay, there is no way you can undergo a transition. To undergo a transition or to understand transition, you need to take a superposed state where these are the stationary states and This state, superposed state, is it a eigenstate of Hamiltonian? Yes or no? No, it cannot. Okay. So this superposed state is what you formally, I am not trying to put all the quantum numbers, I am calling the energy level m and energy level n, and to understand this transition you take a superposed state and find, in this state you find an expectation value for x of t. You can do that. So this is psi star in the position space, you can try to write. Okay. Formally you could take r vector or r of t and do this. In one dimension you could take x, because this is not a right way of writing. If I write the volume integral as dx, dy, dz, I should write psi star, or I should write dv volume in r theta phi coordinate, and then I can put a radial coordinate expectation value. Okay. X you take the radial coordinate is what I am saying here right now. Take the radial coordinate and try and work it out, the expectation value of the radial coordinate in your wave function, which is a superposed wave function. Please do this yourself and see what you get. Even to, let us not even do this, you do a one dimensional particle in a box, just for a simplest case. Let us take a one dimensional particle in a box, take a superposition of ground state and first excited state, and then work out what is the expectation value of x as a function of time. X will be independent of time if the state was a stationary state, expectation value. Is that right? If expectation value is going to be dependent on time, that time dependence is going to be a function of, oscillatory function of the difference between the energy levels. This kind of tells you something. It's like some kind of a harmonic oscillator positions in classical harmonic oscillator, right? You have a cos omega t. So in some sense you see that this is similar to your harmonic oscillator frequency, with frequency being Em minus En by h cross, even in a one dimensional problem. If you do it in the three dimensional hydrogen atom problem, this formally you have to write N1, L1, ML1, and this one should be N2, L2, ML2, and then do the integration over the volume to find the radial coordinate expectation value. That you can do it sitting in a hostel room, calmly, and you can do this. It's just a straightforward exercise, and basically it will depend on a cos omega t or cos between the energy difference between those two levels, and it will be non-zero in the case of hydrogen atom problem if delta L is plus or minus 1 and if delta ML is 0 or plus or minus 1. This I want you to verify. So will you try to check, take this ground state. So what is the ground state is 1 0 0, right? So take this ground state and then take B times, take the which is r theta phi, and do the expectation value of r of t, which is nothing but, someone call this as the superposed wave function, capital psi. Psi star r psi, then the volume will be there, r squared dr sin theta d theta d phi. Okay, I want to do it at t. I want to do it at r theta phi at t. What do you have to do there? You have to try to write psi at t will be a e power minus I e1 t over h cross psi 1 0 0 plus b e power minus I e2 t over h cross psi 2 1. Is that right? You have to substitute this here. and use orthogonality, everything, and see whether this will be non-zero or 0. Similarly, you put this to be here. I think there are no other possibility. If we had taken 3, then you can check that this is not 0. This is going to be 0. If you take this state, you can show that this expectation value will be, if suppose I take the ground state and this is n equal to 3, but L equal to 2, what is delta L here? Delta L is 2, but the selection rule tells me delta L has to be plus or minus 1. So, for this wave function, if you try to do the expectation value of the radial coordinate, it will turn out to be 0, but for the earlier one which I took this 2, 1, 0, it will be non-zero. Get what I am saying? So, this one has to be plus or minus 1 or 0, and this one has to be plus or minus 1. Yeah, so it's like a harmonic oscillator position which is toggling as cos omega t, with the frequency being the difference between these two levels, and if such a thing happens, there is a radiation with that frequency which is seen. This is the interpretation. Experimentally, the experimentalist tells us that we see only lines if the system is prepared and they can see only the specific L, N and M and the N2, L2 and M2. They say that they can see transition provided L1 minus L2 is plus or minus 1, and they see transition provided delta M which is plus or minus 1 or 0. I am asking you to mathematically verify using your orthogonality property that the expectation value of this position operator, radial component of the position operator, as a function of time, which in general behaves like as if it is the harmonic oscillator, is proportional to cos omega t. That is all I am trying. If that coefficient which multiplies cos omega t is 0, then that is a justification why such a transition was not seen in the lab. So, this is what is called as a kind of stringent selection rules, that from one state to another state, even though the energy, suppose from an excited state to the ground state, even though the energy allows that it can decay and go to the ground state, there may be some kind of a stringent condition in the system which will not allow it to go to that. If it goes into that state, mathematics will also help me to show that expectation value of this position or the radial coordinate of this operator satisfies this condition. It is non-zero. Okay, this is the way I try to interpret from theory what experimentalists see. Another way of saying is that there are also other conditions like the potential energy is dependent on 1 over r potential, right, in the hydrogen atom. These are central force problems, and you can show that if you do a parity transformation. What is parity? Just do a inversion. Take an r vector and make it to minus r vector. Does the Hamiltonian change? It's similar to your symmetric potential problem I was telling you. V of x is equal to V of minus x in one dimension, and what did that reflect in your wave functions? That made your wave functions to be either odd functions or even functions. So, there will be a similar argument here that L equal to 0 and L equal to 1, sorry, both. If this is L equal to 0, then it is impossible for such a transition to happen because of this parity constraint. It can be seen independently. Right now we are not doing that symmetry. I am not bringing in that symmetry, but I am just saying mathematically if you do an explicit integration, it turns out to be 0, but you can also argue by that. Okay, we will do these things. We will come to it. We will try to write in the Dirac notation, and it is very interesting to see that there are ways in which you can see the selection rules in a beautiful. You can explicitly do that and check whether it is 0 or not, just for the. Okay, so formally even in one dimensional problem, you can try to say that the expectation value is proportional to this, but if you do the 3-dimensional hydrogen atom problem for the radial coordinate for a superposed state, then you can try to see that there is a time dependence and it will be non-zero only if delta L and delta ML satisfies the selection rule. As he was trying to say, suppose you take this to be 1 0 0 and 2 0 0, will this be 0 is the question, and I want you to verify that. Okay. Use the orthogonality of your associated legender, associated legger, and make sure that you can verify and see whether it will be 0 or non-zero. You can see trivially that there is a cos theta there coming up, and when you do that integral sin theta cos theta d theta will be 0, okay, but you can do it yourself. Okay, so this evaluation can be interpreted as a displacement of an oscillator with frequency omega. This is what I have been trying to stress, with the difference in energy between the two levels, and h cross omega is this, okay.